Okay, so what you've learned in the previous part of this chapter is the kind of the nice situation when you've got constant loads, point loads, UDLs over part of the beam, linearly varying loads, and it can actually handle kind of more complicated things like quadratic loads. So that'd be a kind of the load that looks like a parabola or anything that you have a formula for. But there are scenarios where the loads are different to that again, and well, what do you do then? So let's look at some examples of what I'm talking about. And this is so these are basically scenarios where you either can't write down a loading equation because you can't write down a formula for the load easily, or you can or one theoretical ones that aren't really realistic but mathematically are interesting, where you can write down a formula for the load, but you can't anti-differentiate the function. So these are the two scenarios. Okay, so let's look. So consider this load on a fixed end beam. Suppose you want a formula for the maximum deflection of such a beam under such a load. The formula should depend on the length of the beam, the properties of the beam. These are captured by E and the second moment of area. The material comprising the load can be, so what material is this? Can be captured by a load per unit length factor. This means you're looking for a formula for the maximum deflection in terms of the material here. Now, the question is, how does this load change when you change the span? Is one I'm going to kind of skip over really. But you're looking for a formula like this. Theoretically, this isn't difficult. You find the load per unit length at each point and solve the fourth order differential equation, and somehow you maximize the solution. But you have a problem here. You don't actually have a formula for the load per unit length. So one thing you could do would be to fit a curve to the data. So basically find out what's the load per unit length at distances along the beam, fit a curve to that, and anti-differentiate your mathematical model. The load per unit length would be proportional to the height, so that'd be no issue. Okay, so what you do is something like this. So you measure the height of the logo, perhaps at 10 centimeter intervals, something like this, to get XW data, and then fit a curve to the data. Okay. So now it'd be a bit complicated because you've got this bit and this bit are a bit different, but look, it can be done. So for many bespoke loads, so what a bespoke load is something that's, just kind of a one-off kind of a load that doesn't come into a combination of constant UDL, point load, uniformly varying. For example, a load might not have much symmetry nor pattern, unlike the McDonald's loads. In this section, we'll see how to approximate the shear. Now we'll just go to shear, but these techniques can be gone further to find the bending moment, etc. This would be done. I actually teach this material. You need computers to really properly to second year level 8 mechanical engineers. But yeah, okay. So what we'll just work with is, given the load, how can you find an approximation of the shear if you can't solve the equation exactly? I mean, the normal situation is from earlier, dv dx is equal minus the load per unit length. But there's two scenarios when this doesn't work. You don't have a formula for the load per unit length, or there you have a formula but you can't actually anti-differentiate it. We'll talk about that a bit later. Suppose you're interested in the McDonald's load and the beam spans 6 meters with a total load of 190 kilonewtons. As before, the distance along the beam and load per unit length can be measured and recorded. An engineer goes off, makes a data set, say something like this: 0, 10 centimeters, 20 centimeters, 30 centimeters, 40 centimeters, 50 centimeters, load 0 kilonewtons per meter, etc. Now you want to find the shear force. Using the methods of this section, you can do that. So for actually what this is what the shear force looks like. Something like this. Here you can see, I think there's this little typo here. This should be 180 kilonewtons. Because it's symmetric, the RA and the RB should be equal. We're not going to put this on a cantilever. So they're 90 and RB is 90, but of course it's minus because it's over there. Shear is equal to 0 at the midpoint, so the maximum bending moment occurs there. So our job will be to, given data like this, to kind of create plots like this. Yeah. Now, the thing is actually, of course, these notes are designed for a written exam, but you're going to have an assignment. So what it means is the examples are going to be very, very basic, and you're going to have to extrapolate what's going on in the assignment, as happens in normal years. So here's the other possibility that poses a problem. So you have a load given by a function that you can't anti-differentiate. This can actually happen. So if you have basically any function, you can differentiate it, but not everything you can anti-differentiate. Now, it has an antiderivative. The problem is you can't write it down as a nice formula. So for example, e to the minus x squared, you can't write down a nice formula. Even you can do like an infinite sum, but you can't write down any nice formula which you differentiate to get e to the minus x squared. So you're in the similar, these are the two situations. W of x is given by data rather than a formula, or it's a function that has no antiderivative. It's impossible to solve this in the sense of obtaining an explicit formula for the shear. And this section we showed, despite the absence of an explicit solution, so that means like that you can calculate the shear at any point x. We're just going to find it at, say, 0, 10 centimeters, 20 centimeters, etc. We still learn a lot about solutions through a graphical approach or a numerical approach. Now, probably in recent exams, I haven't pushed the 3-term Taylor method. This might come into the 4th assignment, but I don't know yet. I think I'll leave it off the 2nd assignment. This material really belongs to chapter 4, but obviously I want to apply it to beams, so I have it in this one. Okay, so the direction fields. So let's see what we got. Suppose we were asked to sketch the graph of the shear given by this. Now maybe, could we make some kind of a plot of this? Actually, what I... probably should, if I got... No. Not ideal, and I might be able to make this up on the hoof. And it doesn't say how long the beam is either. I'll just start it off. I don't actually know what it looks like in total. So at x equals 0, it's the W is 10, because the W is actually 5 cos x squared over 6 plus 5. Sorry about this. I just want to give you a picture of what the load looks like, and I'm not even going to be able to do that. So at x equals 0, that's 10, and then when x gets bigger, cos gets smaller. So how far it goes in terms of wave, I'm not sure. It depends on how long the beam is. We can differentiate this. That'll be 0. And this will be like sine x squared over 6 minus 5 sine x squared over 6 by, I don't know, minus or 2x over. I think the point is if at x equals 0, it'll be 0, so it'll start flat. I think it looks something... and it goes down to 0. Oh, I'm not sure. It might do something like that. But look, I'm not sure. Some weird load, something like this, okay? I should probably include that for next year, but anyway, that's next year's problem. Doesn't say how long the beam is, which isn't great, because where does the V of 0 come from? That's plucked out of thin air. Realistically, what you're probably only really going to be able to do these exactly when you have the total load. You estimate that somehow, and it's symmetric, and so RA will be half the total load, and V of 0, by the way, is the same as RA. If you don't have that, you have to do more complicated methods that we're not going to look at. So finding this number is actually an issue, but I'm always going to give it to you. I think in the assignment I give you a kind of complicated load, but it is symmetric, and I tell you the total load, and RA is just half the total load. Okay, so this means the shear is 20 when x equals 0. We don't know a formula for the solution, so how can we possibly sketch its graph? Oh yeah, it's looking for a sketch of the graph of the shear without even like doing any numerical method. So let's think about what a differential equation is. And the equation, this tells us that the slope at any point, so remember that the derivative of shear is the slope of the shear. And remember what slope means, like 0 slope, positive slope, negative slope. is equal to minus the load per unit length. In particular, because the curve passes through the point 0, 20, x equal to 0, shear being 20, its slope there, substitute x equal to 0 into this, you get minus 10. So what this is saying is that whatever the shear curve looks like, at x equal to 0, its slope, if you substitute x equal to 0 into this, you get out minus 10. So the slope of the shear curve is minus 10 at x equal to 0, so it's going down. So we get something like this. So a small portion of the solution curve near 0, 20. And what do I mean by 0, 20? I mean distance equal to 0, the shear is equal to 20. That's given in the question. That the graph of the shear looks something like this. Okay, so whatever is going to happen, whatever the solution is, it starts off in this direction. And this is where this direction field comes from. So as a guide to sketching the rest of the curve, let's draw short line segments. So just go to loads of different points, calculate what the slope would be at that point, and just draw a little line segment in that direction. And that's called a direction field. Now you'd never do that by hand, you do it with some software. Now I am actually not going to ask you to do a direction field, but it's good just to help your understanding of what we're going to do with our numerical methods where we actually get numbers. So there's two words you should be familiar with: quantitative and qualitative. So quantitative is like numbers and stuff. Oh, what's your approximation for the shear force 1.2 meters along the beam? Qualitative would mean, oh, what's the shape of the curve? What does it look like? So that's qualitative, it's not quantitative. So if we do that, we get something like this. So the point that we do know is on the solution is 0, 20. And that's a slope of minus 10. So this is calculating the slope at different points. I think this is somehow supposed to be an x equal to 6 beam, but I can't be sure because I don't really trust that r equal to 20. So here, let's say around, it goes flat. So that would be at, I think, I should be able to do this. So I know at 90, which is pi over 2, cos is equal to 0. So I'm going to try something here. So x squared over 6. So when the thing in the cos is 90, which is pi over 2, cos of it is equal to 0. Is that what I want to do? No, in fact I want it to be minus 1, do I? Yeah, which happens at pi. So multiply both sides by 6. Let's just do our equations properly, and then we do square root both sides. We get x is equal to the square root of 6 pi. Now we'll learn, maybe not in this, but maybe later on, this has two solutions, so it's plus or minus, but we're only interested in a positive x because a negative x is not on the beam. So let's approximate the square root of 6 pi. 4 point, well, on this we can only see two significant figures, 4.3. So at about 4.3, all along this point, let me just come over here, we know that the slope, so the slope of the shear at approximately 4.3, which is approximately square root of 6 pi, which means x squared over 6 is approximately pi. So this is approximately minus 5. So I said x squared over 6, approximately pi, minus 5 cos pi minus 5. And cos of pi is minus 1. So you get minus 5 by minus 1 is plus 5. 5 minus 5 is equal to 0. So what I'm saying is that the slope of the shear is 0 here. So here you can see that around this point, the slope of the shear is 0. And can we talk then? Yeah, we do know that. Isn't that where the maximum bending moment is? Isn't it? So M max. So this is what I mean by well, that's qualitative. That that's kind of a bit of both. So the maximum bending moment where the shear, which is the same as the derivative of the bending moment, is equal to 0. And in fact, I'm talking nonsense because this isn't where the shear is 0, this is where the slope is 0. So we're looking for the point. So the shear is going to follow these lines. So we draw it. Do you see what I mean by following the lines? I'm going to do it below here, so I'm going to cheat. Something like this. So apologies, not here. We might go back and say, what does shear being 0 mean? That's where the maximum bending moment is. Where is that exactly? We don't know. That's what makes it qualitative. We do know that the derivative of the shear here is 0. So that means that actually at this base, the derivative of the shear is minus load per unit length. So this is a place where the load per unit length is equal to 0, or approximately 0 near there. So these are all kind of things you can do. I don't know, can you see bits of stuff you might have done in structural modules here? Probably not, because you wouldn't introduce these weird loads. Okay, so for example, the line segment at the point 2,5, that is, I think, something like that anyway, has slope. So you put in x equal to 2. By the way, you have to be in radians. If there's any differentiation with sine and cos, it has to be radians. So put x equal to 2 into this, you get out minus 8.99. So the slope there is minus 8.99. The direction field allows us to visualize the general shape of the solution by indicating the direction in which the curve goes through each point. So you can sketch the solution curve through the point 0, 20 by following the direction field. And also, we've drawn the curve so that is parallel to nearby line segments. So you've got a rough idea of what the shear looks like. Now, let's be a bit more, let's get some numbers going. So the basic idea behind direction fields can be used to find numerical approximations to solutions. So approximations, we can't solve it exactly. If we could solve it exactly, we would have a formula for the shear at every single point. And if we want to know what's happening at x equal to 2, we just substitute in x equal to 2. And we have it. Here, we're going to have to just make do with approximations. Now, numerical just means the same thing. Really, numerical approximations here just means approximations. We'll illustrate the methods on the initial value problem here used to introduce direction fields. Differential equation tells us that the slope at 0 is minus 10, so the solution curve has slope minus 10 at the point 0, 20. As a first approximation to the solution, what we can do is we can just say, okay, let's say it looks like a line here. We have where it cuts the y-axis, 20, so that in terms of mx plus c, we have the c is 20, and m is the slope. What we just said, the derivative, remember, is the slope, so derivative is minus 10. So this is minus this is mx plus c. Slope is minus 10. C is where it cuts, is 20. So hopefully we have a picture on the next page of this. Yeah. So actually here is now I don't know how exact this is. I'm going to say it's accurate rather than saying it's exact, because you can't solve that thing exactly. So this is the accurate shear, and then this is the tangent, because that's actually what we're using. Well, I better be careful. This is a line. Okay, now in this case it is the tangent. Maybe I'll just write this tangent line. But what happens is we're going to move away, we're going to start using lines rather than tangents. So the tangent at 0, 20 approximates the solution curve for values near x equal to 0. Now that's kind of stuff that is going to be explored further in chapter 4. So Euler is I think he's a Swiss dude, born in the 1800s, whatever. He did all the maths. Euler's idea was to improve on this approximation by, rather than just saying, oh, the shear is approximately minus 20x plus 20, because shortly that will no longer be a good approximation. So like if I do minus 10x plus 20, what do I get? Something like, I just look, just to compare. No, it does go through 2. So it's a good approximation near x equal to 0, but as you go past here, look, the approximation isn't good. So these are errors. So this is an error in the shear, the error using the tangent rather than Now this is not the exact solution, this is an accurate solution. So Euler's idea was move along the direction field as such, stop, change direction, go another bit according to the direction field, stop, change direction. That's basically his idea. For us it'll end up just being a little formula. So Euler's idea was to improve on this by going only a short distance along this tangent line, then making a correction by changing direction. So hopefully there's some picture. Oh no, all the pictures are gone. That's the balls. That's such a balls. I would have made lovely pictures, but look, we'll do our own picture, sure. So what Euler said would be maybe, I'll just do an exaggerated one here. Sorry about this now. So X shear force. Now this is going to be the theoretical exact solution. So what, no, that's gone down a bit too, something like that. So he'd said go along it for a little while in a straight line, stop, see what the slope is at that point, go along for a little while, stop, what's the slope, stop, what's the slope, or looky there, stop, what's the slope, stop, what's the slope. And so you get this, and hopefully I have a picture of something like this somewhere, something like this. So find out what the slope is, go along that for a short distance, stop, ask what the slope is according to the direction field at the point you're at. And you can always do that because you have the differential equation which says the slope at every point in terms of x and y. So that's why you can do that. So Euler's method says start at the point given by the initial value, which would be the 0, 20, proceed along the tangent for a while, stop after a short time, a short distance which you choose, look at the slope, the new location, and proceed in that direction. Keep stopping and changing direction according to the direction field. You don't get an exact solution, you get approximations. But if you want to make the step size smaller and smaller and smaller, which means more and more calculations, you get better and better approximations. Okay, so we'll do the general theory here. For the general first order, so this means dy dx in terms of x and y, with an initial point here. The question that you'll be doing will be, it won't be y and x, it'll be shear and x. You want to find approximate values for the solution at equally spaced numbers. So these should be x0, x1, x2, x3. They should be equally spaced, x4, x5, this kind of thing, like this. So I think this is 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. And you get approximations at each point. What have we got here? So what the hell am I going to write down here? I think I'm going to write down the tangent line, I think. So the tangent to the exact solution, y of x, at x equal to x0. So there's a theoretical, now I'm doing it with y here, but for us it'll be with shears. This theoretical exact solution, we're going to find the equation of the tangent, and we can do that because the differential equation gives us the slope and the point gives us the starting point. So let's do an all y minus y1. Maybe I'll just write down y minus y1 just to make it familiar. So the point, and you want to end up with y in terms of x. So the point you know about is y0, just the roll of 20 up here. We're just doing it generally just to show you the formula. The slope, so the slope will be given by the differential equation. So the slope is given by the differential equation, which the differential equation changes, of course, because the load changes, the formula for the load changes, the differential equation changes. So you just substitute in, for us it'll be x equal to 0 almost, but theoretically you sub in the starting x value and y value, the 0 and the 20, times x minus the other x, the point you know about is x0. Now what are we going to do? We're going to add y0 to both sides, and we're going to get y0, so the starting y value, plus x minus x0 times the slope at the starting point. Okay, now when we do the examples, some of this, it'll be easier to do even if you don't fully understand it. My recommendation is to try and understand it though, but I appreciate there's lots of notation here. So what we want to do now is we want to find out what's going on. So we have the initial point, which is x0, y0. I want to find out what's going on at x1, where the true solution is y of x1. And what we're going to do is we're going to travel along. So the true solution might look something like this. And we're going to travel along the tangent. And what we're going to say is, we said a short distance, we're going to call that distance h. So it'll be x0 and x0 plus h. So we're interested in what's happening at x1. So we're going to substitute it into this yoke, x equal to x0 plus h. And so this x minus x0, if you take away x0 from both sides, x minus x0 is equal to h. You end up with the following formula, that the y value, according to the line, this black line, the tangent, is the previous y value, the starting y value, plus the step size times the slope at the previous point. And that's essentially Euler's method. So this is approximates the y value